Okay, guys. Okay. Welcome back. For those who have not joined in the first half, I am Krishna Balasubramanian. and we are having this short course on physics of nanoelectronics. In the first session, it was a rather simple and introductory session. So we spoke about history of charges, electronic experiments, understanding material matter, and we saw particularly kinetic theory of electrons, that is the Groote's model, conductivity in metals. We saw what is it that it is trying to get to. It gave a particular example, or it is able to explain Ohm's law for some materials. It gave a feel for what is resistance. Resistance should inversely depend on the number of carriers that you have, also the time scale. If the characteristic lifetime is small, if tau is small, tau is called the characteristic lifetime. If tau is small, you can see the conductivity is small. If the conductivity is small, that means that you get scattering much quicker. So let's say instead of tau can be 1 microsecond, tau can be 1 picosecond, which will have a larger conductivity. If I ask you this question, obviously it should be 1 micron, right? A larger tau should have a larger conductivity. Why? Can anybody tell me physically why larger tau physically gives you larger conductivity? Okay, I'll give you time to think about it later on.
Lesser scattering.
Sorry?
The scattering will be less.
No, tau tells you what is. So let us take, I take an electron, okay, some random electron. After what time will it scatter is tau, okay? And if I'm saying tau is longer, why is conductivity higher?
Sir, because collision is less there.
Okay, why less collision means more conductivity?
Particle can move without any hindrance, no?
Why? It's fine. Okay, it's moving. It will be, if it goes at a constant velocity. Why does it matter? It's going at a constant velocity. The velocity is constant. See, this v is constant. Current will be constant. Why do you matter? Why do you care?
Sir, mobility will be more, no?
Mobility is tau, no?
Tau is the time, no?
How is the time? But what is mobility?
Mobility is
So mobility comes from this relation. V is equal to mu e. Correct. So mobility is just E tau by m is mobility.
So tau is relaxation time.
Yes. So I am asking why larger tau means better conductivity. Physically, I mean, from the equations and all is different. Physically, let's say you go into a material, put a microscope and take a look at how the electrons move.
Yes, the electron takes more time to move from one place to another place. It gives more conductivity, sir, because it takes more time to change its position from one point to another point. So that's why the conductivity is more, because the lifetime of the electron is more, because if tau is more, sir.
Yes. See, what is happening? What is happening in between taus? In between two scattering events, what is happening?
Recombination?
No. We are not even talking about recombination here. So between two scattering events, there is a force and the electron is accelerating. So between two scattering events, the velocity keeps on increasing, right? So if tau is large, the net velocity that the electron will reach will be large. So basically, physically, what I'm saying, if you take a look at if each of the electron in the material, from one scattering to the other, there is a field, and it starts accelerating. So velocity keeps on continually rising up. At the scattering point, the velocity now changes again. So the longer an electron goes without scattering, the higher the velocity it will be able to achieve. Right? So physically, that is the reason why you want larger scattering times. You want fewer scattering, because the net velocity, the net average velocity will be high. That is because the maximum velocity that an electron reaches is also high. Remember, there is a difference between maximum velocity and the average velocity. Well, let's not get into it, but you should also remember that. All right. Acha, chalo. So let's go back to our discussion. We already spent a lot of time on this. We have much less time for the other things. From now on, we are going to take things a little bit more serious. So it's going to be a little bit more involved. So I kindly beg your attention. All right, it is 3:45, and this is what somebody asked me also. So let's get going. So we saw about crystals, 3D, 2D, and how to grow them and stuff. The most important property of any crystal is symmetry. And what is symmetry? Symmetry is, which is, so you go to one point and you do some activity, something. You rotate yourself, you translate, you do mirror, you do something such that the entire environment of the atom does not change. So you go from here to go to next atom in the same lattice. From O, let's say you go to this point and take a look at it. Of course, assume that this is an infinitely large set of points in all dimensions, right? You go from here to here, it remains just the same, correct? Does it remain the same if you go from here to here? Yes. You have an electron here, you have an atom here, and you have another atom. So these two are also symmetrical. But if I rotate by 90 degrees, is the crystal symmetric? So from here, I go here and I start looking from this direction. Does it look symmetric? The answer is no, right? Why? So let's say I look from this direction and I look from this direction. Will the crystal look the same? If I look from this direction, there is an atom in A2. If I look from this direction, there is an atom at A1, and A1 and A2 are not the same, right? So
Yes.
this kind of a structure is not symmetric for 90-degree rotation, but whereas it is symmetric at 180-degree rotation. If you look from this direction and if you look at this direction, both of these will look the same. So there are certain movements that you can do in which the crystal remains symmetric, certain movements that you can do in which the crystal does not remain symmetric. It can be rotation, it can be translation, it can be, so translation we already saw, it can be rotation, it can be inversion, it can be reflection about a plate, it can be identity. Of course, this is coming from mathematics of group theory. So when you use mathematics of group theory, the group should be closed. So you also add an activity such that you do nothing. Nothing is also an activity, right? Because zero is also a part of a group. You should have zero also. Our famous invention of the Indian thing, right? So identity is not zero. Identity is one. But I'm just saying null, action of null should also be included. So that is also here. In case of an arrangement of atoms having translational symmetry, you can define a vector called R such that any function defined at any point, so I take a point here and I define a function like potential or something of the sort, velocity of the electron, which has a particular shape. this shape should remain unmodified if I take some vector r, which is some a times x plus b times y, right? Some translation. You move some translation such that it does not change. It will have to be it has to do with what is the translation symmetry, the minimum translation symmetry that you can do, right? So you account for this a1 and a2. Sorry, it should not be like this. It should be l1 a vector, a1 vector plus m1 a2 vector. This is what your r will be. This r is basically the translational symmetry vector. I translate from any point r, which is a linear combination of these two. I will reach a point in which the function remains the same. It's called translational symmetry. A volume in 3D or an area in 2D can be chosen, which gets repeated, right? So let's say if I have an atomic arrangement like this is symmetric. Here, what I look is the same as what I look from here, right? So it is all symmetric everywhere. There are different ways in which I can choose to look at. I can take a look at an area like this, which repeats in space. There is a parallelepiped as I shown here. You can take a look at this area, or you can do what is called as a Wigner-Seitz cell. What is a Wigner-Seitz cell? You take perpendicular bisectors of all lattice vectors. So this is one lattice vector. You take a perpendicular bisector, second lattice, third lattice vector. You take all the perpendicular bisectors. The area enclosed is called as a Wigner-Seitz cell. You can take this one also. So basically, your definition of an unit cell is not unique. It's not unique. An unit cell should have only one point. So we're talking about lattice. Lattice are mathematical structures. These three dots at each of these points are called as motifs. So at each point, you can either have these triangles, or you can have a rabbit, you can have a rat, you can have whatever. At each of these points, you repeat the same thing. If you have a rabbit here, you should have a rabbit here also, right? Each of these lattice points says it's a mathematical structure. At each point, whatever is there in the previous point, it just gets repeated. That's what this says, right? So like this, there are different systems of symmetry. A Bravai lattice is one in which you have only one lattice point per unit cell. There are different Bravai lattice points, lattice systems, Bravai systems. The simple cube, which is defined all of them having perpendicular vectors, all of them having the same dimensions. We have what is called as a body-centered cube. In each of these cube, you add an atom or a lattice point at the center, right? It's called a body-centered cube. For a body-centered cube, the lattice vectors, by the way, I don't know if I have defined the lattice vectors before. What is a lattice vector? It is a step that you can take in a particular direction in which the symmetry is retained, right? So from here, I can go to the body center in which the symmetry is still retained. How do I go to the body center? I take 1/2 along x, 1/2 along y, and 1/2 along z. Then I go to the body center, right? So these are three vectors: ax, bx. A is ax, b is ay, c is a by 2 into x plus y plus z. X, y, and z are three orthonormal vectors. There are two ways to define this lattice, as we saw previously. This can be one way. A second way is you can define them from each of these. So you can take three of these body center points from the origin, and each one of them can be a lattice vector. Certain materials such as iron, potassium, barium, all of them crystallize in this body centered lattice. An important structure is called the face centered cube. You take a cube, and each of the face you add another lattice point. By the way, I think I should tell here, a lattice point is a mathematical structure again, where you can add anything that you want. As I said previously, it should just repeat, right? So in the previous thing, oops. So in the previous thing, each of these things are lattice points. In the cube, you have lattice points on the edges of the cube. In the body center, you add additional lattice point at the center. In the face center, you have additional lattice points at the edge of each face, right? So you add 6 more lattice points. So each of these vectors, this north, west, top, bottom, uh, north, south, east, west, top and bottom. This is what I have nomenclatured here. So each one of them will be A is A by 2, Y plus Z, right? If you want to go to this face, you take half in X, half in Y, you get this point, right? So like that you can do. There is another structure called hexagonal closed pack structure. I'm rushing through all these things because these are information that you can probably get in any book. But all that I'm trying to show here is to distinguish between a lattice and a motif, which of course, if you have seen, now you can understand what is FCC lattice with a motif. So the black one is a cube, which is an FCC lattice. At each point, I add another atom. For each black for each black atom in each of the black lattice point, I add a red point as well, right? So what it gives me is, it gives me another face-centered cube which is offset. So basically, this is also a face-centered cube, but with a motif, right? So at each lattice point, now I have 2 atoms. So many semiconductors crystallize in this structure, particularly silicon, germanium, diamond, zinc sulfide, gallium arsenide, indium phosphide. There is a particular important reason. Still now, we have not talked about semiconductor metals and the differences between them. I assume you guys have known something about them, so I'm just going to give a small intro here. You see, the previous FCC, you have all the metals, right? Copper, silver, all these things forms FCC. FCC with a motif. Once you have a motif, that is, you have 2 atoms per lattice point, you form a semiconductor. Why? There is a particular importance here, right? So we will see why this is so. So silicon has 2 atoms per lattice point, germanium also similarly. In silicon, germanium and diamond, both these atoms are the same. Carbon, carbon for diamond, silicon, silicon atom for silicon, germanium, germanium atom for germanium. But if you have 2 different atoms, zinc, sulfur, gallium arsenide, indium phosphide, red and black are different, then you have the other zinc sulfide structures, right? Now that we have seen about structures, crystals, and symmetry, the additional important thing that you should know, and which is of paramount importance, is the periodicity. What is periodicity? You take a point, the function, any function, right, which looks the same if you move a particular distance. So L here, you take a function in X, you have something like this, a wiggly structure. You move in X, L, some L distance, it starts repeating. This is called as a periodic function, and you write something like this. So you know that periodic functions can be written in a Fourier series. So f of x is written as some Fourier series. So Fourier series are summation of exponentials, right? E power I 2 pi nx by L. So these are all some sinusoids which you can add up. Fourier series just tells you that if you have a periodic function, you can represent it by sum of sinusoids with various frequencies. Now, I just take this Fourier series expansion and replace 2 pi n by L as some gn. Remember, 2 pi by L is already some sort of a spatial frequency. L is periodicity in the real space. 2 pi by L is a periodicity in the frequency space. Frequency is typically defined for time. If you talk about space, then its conjugate inverse is called as reciprocal space. I think you understand. You take time, inverse of time is frequency. You take space, inverse of real space, x, y, and z is called as reciprocal space. This is the relevance. So here I am already talking about 2 pi by L. So this gn is already in the reciprocal space. So this summation is now written as f of x is summation over all g, summation over all frequencies, ag the coefficient, e power igx. G lives in the Fourier space. Fourier space, reciprocal space are two different ways. Now I substitute this into the periodic function. If I substitute, I come up with a with a condition for periodicity, which is e power igl equal to 1, right? So if I put f of x plus l, f of x is this expansion, put x as x plus l, summation ag e power ig x plus l, right? You get this. Now e power ig x plus l should be equal to again f of x. This is what this periodic function definition tells you. This can be only true if e power igl equal to 1. When will e power igl be equal to 1? When the e power I followed by whatever is there, g into l, is 2 pi. Only then this function will be 1, right? So you know the Euler equation, e power I x is 1 only if x is equal to some integer multiple of 2 pi. Integer can also be 0, remember. So g into l is some integer into 2 pi. Now what g becomes? Integer into 2 pi by l. So here, if L instead of L, we talked about reciprocal lattice previously, we had A and all those things. So now instead of, so here, instead of A1 here, we write L into A1. So that means that it does not have to have just one lattice vector. The responsibility can be, or sorry, the periodicity can be L into some lattice vector in x direction, right? So it is g dot L A1. Whatever that we saw in one dimension here, so here we all talked about only x, can be now expanded to a three-dimensional space. In the three-dimensional space, you have capital R. Capital R can be broken down into L1 A1 plus L2 A2 plus L3 A3. Remember, this comes about from here, A1, A2, and in third dimension, you have A3. These are all lattice vectors. And each of these lattice vectors, L can be some any integer, right? So this here you can move twice A1, thrice A2, and probably 4 times A3, right? You can move all these fashions. So you write f of x is f of r plus capital R. This capital R can be some integers, L1, L2, L3 are integers, integer summations of A1, A2, and A3. A1, A2, A3 are real space lattice vectors. You can see the same thing here. It is again drawn in 2D for us to easily visualize. In 3D, it becomes much harder to draw, but then you can easily imagine some cubic kind of a crystal, right? A1 and A2, these are lattice vectors. Similarly, the Fourier expansion, instead of ag, e power I g into x is what we saw in the previous slide. Here it comes g dot r. I suppose you all understand what is dot product means. You just multiply g1 a1 multiplied by
The scalar product of two vectors, sir.
okay. Is there a question? All right, so I continue. So in three-dimensional space, you get e power I g dot r. I will soon show you how to expand this dot product. There is a particular way in which you expand the dot product, and it is only true if you have g and r being in the same space or having orthogonal vectors. But let's keep it like this. And the substitution in the periodicity will be true only if e power I g dot r equal to 1. Remember, g is in the reciprocal space, r is the real space periodicity. Correct? This equation is a very important equation. You will see this repeatedly. If you have people here who do electron microscopy, they will know this as a Laue condition. You need this to ensure that G represents a reciprocal lattice vector. So we saw remember G is any vector in the reciprocal lattice space, and in the reciprocal lattice space, we write this G as G1, B1, G2, B2, and G3, B3. You have B1, B2, B3 as some vectors in the reciprocal space, right? And how do you do the dot product? It's written like this. Take each one of this component and multiply with the A vector. Second component, multiply with the A vector. Third component, multiply with the A vector. So the total G dot R should have these many components. So how many terms we will get? We'll get about 9 terms on this one simple dot product, which is very hard to really work with, right? That is why we have a very special definition for the reciprocal lattice vector. So we do something clever. We ensure that we take these vectors b1, b2, and b3 such that b1 dot a2, b1 dot a3 are 0. That is, b1 is perpendicular to a2 and a3. Similarly, b2 is perpendicular to a1 and a2. Similarly, b3 is perpendicular to a1 and a2. Maybe I make a mistake. b2 is perpendicular to a1 and a3, and b3 is perpendicular to a1 and a2. Like that, you choose such that you reduce this 9 term product into just 3 terms. So you will get g1 l1 into plus g2 l2 plus g3 l3. So how do you choose this such that b1 is perpendicular to a2 and a3? The best way to do is to use curl. So you do b1 equal to 2 pi. The reason for 2 pi you will soon know, because g dot r should be an integer times 2 pi. For the previous condition to be true, g dot r to be equal to 1, it has to be integer times 2 pi, right? So you take b1 to be 2 pi into aj, here it is a2 cross a3. Just this definition ensures that b1 will be perpendicular to a2 and a3, because this a vector cross product will give you a result which is perpendicular to both a1 and both these two vectors, right? This is what your vector space vector calculus just tells you. So this is the definition of reciprocal lattice vectors. So the bottom line is, if there is any k in the Fourier space can be represented by reciprocal lattice vectors, then there are solutions to the real space lattice. They contribute to the solutions in the real space lattice, right? There are a few properties of the reciprocal lattice. I'm sure you might have seen this before. Any vector in the reciprocal plane is normal to a set of lattice planes. The volume represented by the reciprocal lattice vector is inversely proportional to the volume of the real space. Why is this true? Because of this definition. You ensure this additional division is taken such that the volume in the reciprocal lattice space is inverse of volume in the real space. A direct lattice is a reciprocal of reciprocal lattice. This again comes from the definition of the reciprocal lattice space. And a Wigner-Seach cell of the reciprocal lattice is called as a Brillouin zone. So this is something that we saw previously. Now, let's take a real space. We just now found that for each real space with some periodicity, you can always define a reciprocal lattice as given by these equations. Once you generate a reciprocal lattice, you can obviously find this Wigner-Seach cell, right? So once you have reciprocal lattice vectors, you draw perpendicular bisectors. The area enclosed by them is called the Wigner-Seach cell. The first Wigner-Seach cell of the reciprocal lattice is called as the Brillouin zone. This is also something which you will repeatedly see in solid state physics. So you have a real space lattice, you can always draw a reciprocal lattice. You take a reciprocal lattice, draw perpendicular bisectors to the reciprocal vectors, you will find the Wigner-Seach cell. All right. So now we saw periodicity, we saw reciprocal lattice, and we saw Wigner-Seach cell. We saw the first Wigner-Seach cell and the Brillouin zone. Okay. Now let's talk about electrons in these periodic structures, right? So finally, we are interested in asking this question: what happens to the electrons in a periodic potential? We saw about periodicity. Where does this periodicity come into our electronic structures, right? Is that the question? If you are asking, the answer is coming. This is the famous Schrodinger's equation. I'm not going into the details about why Schrodinger's equation. So in the Schrodinger's equation, there are two important parts. One is H, this H cap is called as the Hamiltonian. It describes all the energies of an electron in the system. The Hamiltonian has two parts. One is the kinetic part, which is minus h car square by 2m into del square. Why is this the kinetic part? Can anybody tell me why is this the kinetic part? Does anybody know? In quantum mechanics, the momentum operator is defined by h by I del, right? So if momentum is h by I del, then h squared del square is p square. So minus p square by 2m is half p square by m. P square is m square v square. So this one will give you the kinetic part. The v here is called as the potential energy. All the periodicity that we spoke previously is being represented by this v. This v is the periodicity of the lattice. So once you incorporate the lattice periodicity into the Hamiltonian, you have to solve this eigenvalue problem, which is h hat psi is equal to E psi. Once you solve the eigenvalue problem, you know where to find an electron in a periodic potential. So this V is periodic in reciprocal lattice, periodic in the real space vector R. So we write this V of any R, any position in the real space is V of that R plus capital R. Capital R is the periodicity of the lattice. Once this is true, we can write this equation. So the H at different points. Let's take this ket. Okay, let me write something. A lot of this and that are being used. Can you hear me?
Yes, sir. Yes, sir.
Okay. Are there any questions? Am I going too fast? Okay. If
No,
there,
sir.
Sir, can this portion be repeated? Electrons in a periodic potential.
which potential you want?
This electrons in a periodic
Electronics in a
potential.
periodic potential. Yeah, that's what I'm coming to. Okay, that's why I've stopped it here. So I will repeat this treatment. Okay, it seems a little bit tricky. So how do I? Okay, let me do this here itself. Fine. So let's take a periodic potential, periodic arrangement of atoms. Okay, this can be any lattice, some Bravai. Okay, it can be cubic, it can be anything, and you're talking about electrons here, and electrons are defined by wave function psi. Does anybody not know about psi? Is there anybody who does not know about the wave function? What is a wave function? Okay, so I assume you all know about psi. Just one thing for people who really do not know about psi is the probability to find an electron is given by psi square. Mod psi square at any point x gives you the probability to find an electron at some point. So I have something like this. Let's say psi square is like this. This is x. Let's say this is 0.5. This tells me an electron is most likely at this point. Half the time it is at this point. The other half the time it is elsewhere. Okay, so psi is what is a wave function. It tells you where the electron is. Once this is given, the actual wave function, how to find an electron, is to solve this equation, which is called as a Schrodinger's equation, which is an eigenvalue problem, which is h psi equal to E psi. Each of this is a ket. And h can be written as a kinetic energy term and the potential energy term. If the structure is periodic, then let's say I'm going to call this at position 0 and I'm going to call this as position r. Okay, the periodicity just ensures h of 0 equal to h of r. Okay, any r. This R can be R1, R2, R3. So the total Hamiltonian is same at each of these points. Once the Hamiltonians are the same, so I replace this here, and this is where I get the H at R. Okay, I write the same equation, the Schrodinger's equation at this point R. How do I write it? H at R, psi, the wave function at R, equal to some E at R, wave function at R. Correct? This is this equation at this point. And we also saw that H of R is equal to H of 0, right? So this one I can now replace with 0. So for the same Hamiltonian, I have, so this is also an eigenvalue equation, right? For the same Hamiltonian, H naught, HR, and something, I have infinitely many solutions. So this R can be replaced by any of these lattice points. So each of these lattice points will contribute to a solution to this eigenvalue problem. And this can only be true. Let me go back to the next slide. So the R is an eigenvalue solution at the 0th point as well as any point in the periodic space. So this is 0. I have several other lattice points, R1, R2, so on till Rn. Because H of R1, R2, Rn, so on is equal to H of 0, all the wave functions at 0, at R1, at R2 are all also solutions at the 0th point. This can only be true if the wave function at any of the lattice point are just scaled versions of the solution at the 0th point. And this can be written only when you write from the Bloch's theorem. This is a kind of a proof for the Bloch's theorem, but a Bloch's theorem can be simply stated as this. If you know the solution of the Schrodinger's equation at any point R, so this is the lattice, each one of them are separated by the R vector, and you know a solution at some point R, right? We call it psi of R. The solution at any other point, which is lattice translated. So the same distance you write at this point also. It is lattice translated by 2R, right? Is just psi of k, of some momentum k, h cross k, small r plus capital R is e power I k dot r. So this is some phase. This is some phase multiplied by the solution at this R. If you know the solution at this point, now you know the solution at all the lattice translated places. You know the solution in the entire space. This is why crystallinity is very important. All you need to know or all you need to solve is just a region inside one lattice translation. Once this is solved, now you know the solution to the entire crystal. Okay, this is what your Bloch's theorem finally says. For any wave function 0 that satisfies the Schrodinger equation, there exists a reciprocal lattice vector k such that the translation in real space R is equal to multiplying by the phase factor. Why is it called a phase factor? Because eventually all you care is only about the magnitude of psi square, and magnitude of psi square is all the phase, all the imaginary parts are lost. This is e power I k dot r multiplied by e power minus I k dot r. So all the phase parts will be lost in the magnitude calculation. So only that matters will be only this size. Okay. I suppose I did. Are there any questions in Bloch? Did you understand what the Bloch theorem tries to tell you? Okay. Okay. So if I have some function at some point here, which looks like this, I know if I lattice translate by R, the function will just be phase shifted. I take the sign. What is phase shifting in sign? I just start at some other point, but the frequency and the amplitude and everything stays the same. So the solution of the Schrödinger's equation at any other lattice translation is just a phase shifted version of things. So you write a solution to a periodic crystal of something like this, psi k of R. Why k here? K is coming because you have a plane wave solution. A plane wave has a spatial periodicity of k. So e power I k dot R multiplied by uk of R. Now, if you put that into the blocks equation, you get to this point where uk of R is equal to uk of small r plus capital R. This is just a different way of writing the same blocks equation. Okay, so we understand these crystals. We understand the wave function solutions in these crystals. Now, we have to understand one other aspect of things. One is, once you understand the solutions of the Schrödinger equation in the first lattice translation, the solution for any other k, which is farther away from the first lattice translation, can be written as a replacement in the same, reduced zone or in the first Brillouin zone itself. So why it is true? Let's take a k vector in the reciprocal space, which is the G is the reciprocal space lattice vector plus some k prime. So let me just write it. So let's take some reciprocal lattice vector like this. Okay, this is G. The real space lattice vectors are called in R's, and the reciprocal ones are called in G's and K's. Okay, if K, that is the reciprocal space vector K, is here, this is 0, right? So the solution, this is the first Brillouin zone. If K is not here, but at some other point here, which is away from the first Brillouin zone, how do you represent this? Do you really have to study this? What the blocks, so this can be written as 2G plus this K prime. We call this K prime, right? So I write K as 2G plus K prime. So this is first G, second G, and the offset from the second G is 2G plus K prime, right? And now I replace this K into this blocks equation. So psi K of small r plus capital R should be equal to e power I K dot R psi K of R, right? So if I substitute this, what I get is this lattice translation is simply e power I K prime dot R. So only this separation from the reciprocal lattice vector is what matters. The entire distance from origin does not really matter. Only the offset from the reciprocal lattice vector matters. That's why people always talk about only the reduced zones. It's called as a reduced zone because you only talk about the first reciprocal lattice. Any point away from the first reciprocal lattice can always be represented by a point inside. Right? This is another consequence of the Bloch's theorem. Okay, so we talked about solutions to the Schrödinger's equation. We talked about the periodic potentials. Now let's talk about a very important condition. It's called as the Born-von Karman boundary condition, which says that the k value. So here we are talking about k's. This is in the reciprocal space. So you don't talk about lengths, but you talk about inverse of length. So we talk about 2 pi by L. So this is something that I should also say. So in the real space, you talked about length, right? So you have you have a real space lattice with some periodicity r, right? And you talk about some length L. But in the reciprocal space, you don't talk about this. You talk about another reciprocal lattice, which is separated by r, right? And any point here is mentioned by k, right? And this k is related to real space by 2 pi by l. This is the real space and reciprocal space relation. I suppose uh, uh, you have to get it in place before we go in and then decide and talk about all these things. Okay. All right. So we talked about reduced zone. Now we come to the Born-Warman boundary condition, which tells you what can all be the k values in a crystal. Can the k values be continuous or are they discrete, even in an infinitely large crystal? So if we take a crystal whose lateral dimensions are L, L, and L, these capital L's are the sides of a cube. So I take a really large cube in the real space. These L's can be 1 centimeter. Okay, take L to be about 1 centimeter. What will be the volume of this cube? Will be L cube, right? And in each of this side, let's say that there are about 1,000,000 unit cells in 1 centimeter cube, right? So this N will be 1,000,000. What Born-Karman boundary condition tells you is, he says, assume that you take a crystal like this, which is 1 centimeter by 1 centimeter, as shown in this left blocks. At the end of this block, you assume that you have another crystal of the same kind. Don't assume that the sample ends at the edges. This is a theoretical construct, and this is really necessary for you to handle these structures. Till now, we only know about infinite lattices, right? We did not talk about edges in samples, but all samples have edges. How will you reconcile this? In practice, there are no infinite crystals, correct? For this only, Born-Karman came up with this condition, saying that at the edge of each sample, just assume that you have another sample such that psi, that is a wave function at any point r, plus Ni is a number of crystals, number of unit cells, right? I said about 1,000,000 into Ai, one unit cell edge, that is the edge of this sample. Psi of r plus 1 centimeter should give you the same r here. If you translate by 1 centimeter, you should get back to the same point, right? You have to, so this is an assumption that we get into. Why is this true? It's because of this. The smallest k that you can have here, okay, each of these k gives you a wavelength in the real space, right? K is just k is called a wave vector, right? So an inverse of k is a wavelength. How big a wavelength you can have? The smallest k will give you the largest wave that you can have in the real space. Smallest k will give you the largest wave you can have in the real space, right? So here, let us say this is N1 and this is 1 centimeter square. I have a wave which starts at this edge of the sample. By the time you get to the edge of this sample, the wave better die. What happens if the wave does not die? This is the largest wave in the sample, right? My sample is 1 centimeter square. What is the largest wave in the sample? If the largest wave in the sample is larger than the sample size itself, then you will start having reflections. And you never see reflections in a crystal. So just in a crystal, right? Of course, if you have RF and everything you can have, but just in a crystal, you never see reflections. That's why the smallest k that you can have in a sample is bounded by the Born-Karman boundary condition, which says that you do not have any reflections in the sample, and the largest wave that you can have in the sample goes from edge to edge in each dimension. So psi k of r plus Ni Ai this is once again the block equation, right? Translation by a reciprocal lattice should be e power I k into the phase factor into this function. So e power I k into ni ai. If you do this, now you get the smallest k that you can have is 2 pi m will be, let's say m is 1, that is the smallest k, 2 pi by n1. So the smallest wave vector that you can have is inverse of the number of unit cells that you can have in a crystal. So here I have a 1 centimeter square crystal with a million cells. What is the smallest k that I can have? Is 2 pi divided by a million is the smallest k that I can have. So the k is not discrete. Sorry, k is not continuous, but you can have only discrete number of wave vectors in a sample. Right? So the Born-1 boundary condition tells you that the k is not a continuous function, but is discretized. And it is discretized because you cannot have any frequency that you want. Each of these waves should begin and end at the beginning and the ending of the sample. So this k will turn out to be 2 pi into m1 by n1. m1, m2, m3 are all some integers. n1, capital N1, n2, and n3 are the number of unit cells in each dimensions. You have a million unit cell in x dimension, million unit cells in the y, and million unit cells in the z. So this can be, I mean, this gives you any k vector that you can have in a lattice. All right. Okay. Now that we understood the k vector cannot be continuous, k vector is discrete, and the smallest k vector that you can have is 2 pi by the number of unit cells that you can have in any site. Right? With that given, we can ask how many such electrons can you have in a crystal. So that is given by the density of states. Let's take an example of density of states in 1D, and you can extend this to 2D, 3D, and so on and so forth. Okay. So once again, we are going to talk about plane waves, which are given by these functions, psi k, which is e power I kx. And you know the energy values of plane waves are h bar square k square by 2m, right? Do you know, or should I have to explain this? Hello?
We know, sir.
Okay. Okay, great. So now that we know that the psi k's are plane waves and the energy of these psi k's are h bar square k square in one dimension, if there are n1 cells in x-axis, because we're talking about one dimension, we have n1 unit cells in the x-axis, then the lattice constant b is given by 2 pi by a1, right? Because a1 is the periodicity in one dimension. The reciprocal lattice periodicity is 2 pi by a1. What will be the smallest k that I can have? Is 2 pi by n1, right? N1 is the number of unit cells that you have. So the smallest k that you can have is 2 pi by n1. So the number of states that you can have is dk. I take a small small cut in the x-axis of dimension dk, right? So the number of states that I can have is dk divided by what is the smallest unit that I can have? 2 pi by n1. So dk by 2 pi by n1 is the total number of states that I can have, and each state can have 2 electrons, up and down spin, right? I did not go into the details of the quantum numbers, why you can have only 2 electrons and such. I suppose those things are probably we could have covered this in the first 2 lectures. So given a small space in the k space, given a small region in the k space of length dk, how many electrons that I can have is what I'm trying to calculate. So basically I will be having dk divided by 2 pi by a n1 number of states and number of electrons. Sorry, so this is on one side, positive k direction. On the negative k direction, you have another dk by 2 pi by a n1. So total number of states of dg will be 2 times dk by 2 pi by an1. Once you know dg is the number of states that you can have. You can so basically you get by dg by dk, but density of states is written by dg by de. So you can replace dk by de. How? You differentiate this equation. E is h bar square k square by 2m. If you differentiate this, you get h bar square k by 2m into dk. So you replace dk in this equation by de. You will finally get what is dg by dg. dg is the number of states per unit energy. dg by de is number of states per unit energy per unit length, because we're talking about 1D, will give you this expression, which tells you that it goes inverse of root E. So as E is low, you have infinite density of states. As the energy level increases, your density of states decreases. This is what happens in one dimension. All right. So the green line here shows the density of states in 1D. The same thing can be carried forward for 2D, right? In 1D, we took 2 strips of lines, which is dk. In 2D, we have to take a ring, right? So we take some k and see how many states we add if you take one step dk from this ring. Maybe I should draw this here. Okay. So if the previous slide was not clear, let me at least clarify this slide here. So what we are trying to say is, I take some k in a 2D space. This is 2-dimensional space. I take some k, and this k in 2 dimension will represent a ring, right? A circle, and you have some states. From this k, I take one small step of distance dk. The question is, how many states do I add? This is the density of states in 2D. I take a small step from the current k value of dimension k. How much do I add? How do I find this? How do I find this area? This is
Sir, outer circle area minus inner circle area.
good. Or you can also use the calculus, which is 2 pi into k, that is the circumference of this, multiplied by this small change dk. Okay.
Yes. Yes.
Both of them will give you the same value. So this is the extra area that we add if I take this step dk. Now I add this extra area. In each of this, in this area, how many states can I have? How do I find this? I take this area and divide it by the smallest k area that I can have. And what is the smallest k area that I can have? Which is 2 pi by an1 into 2 pi by a2n2. This is the smallest k space in the 2 dimension. Smallest k in the 1 dimension was 2 pi by n1, correct? So the smallest area in 2 dimension will be 4 pi square by a1 a2 into n1 n2. So this I divide by this. This is what is the total addition of states if I take one small step, right? With this given, I once again do the same trick that I did previously. Convert dk to de. Divide this expression, differentiate this expression, convert dk to de, substitute that. I will get what is the additional state dg by de per unit area. The funny aspect of things, in 2 dimension, it is independent of energy. So this is a very important conclusion. The density of states in 2 dimension is independent of energy. The density of states in 1 dimension had this funny shape, which went like this, right? Exponential at e equal to 0 and goes and reduces at higher energies. In 2 dimension, the density of states is constant.
Sir, how it represents a step function?
Which
In
function?
in books it's written, sir, in that density of state function in 2D looks like a step.
Correct.
So how does it represent, sir, a step?
So
It's a constant
how,
line.
how is this constant represents a step?
I mean, in the book, they are writing it represents a step. Okay.
Right.
So how does it justify that?
So I
I mean, why they are writing that step?
right. So I will get to that. Okay.
Yes, sir. Yes, sir.
So the in one dimension, let me get here. Okay. In one dimension, the density of states looks like this. So if I plot it, I can either draw or write. All right, let me plot here. Okay. In one dimension, the density of states looks like this. Because each one of these things are bands. In each band, k values go from 0 to, so this k value, so this is this k, right? And this is one band. You have several such bands. So each of this band will contribute a state, which is like this. So what happens? I will clear and again draw. In 2 dimension, the first band will give you an energy which is constant. This is n equal to 1. And the second band will kick in at some energy level, which will make a jump and again give you a constant energy. The third band will kick in at E3, will give you a jump and give you another energy. So in each of these bands, the density of states is constant, irrespective of what energy we are talking about. But each time you reach a point in which you add an additional band. So this is 0th band, this is the first band, and this is the second band. In one, so this is 2D. The one dimension one will look like this. Can somebody say how the 3 dimension will look? The 3 dimension will go like this, parabolic.
Yes, sir.
Okay, you get the point.
Sir, is it for different values of k?
So
You
density of states we draw from energy. So
energy,
density,
yes, yes.
it
Yes,
is
sir. That that
so
I got, sir. Yes, yes. No,
for each,
when
wait, I'm getting at.
yes, yes, sir.
At each energy, you can define 1k. They are related, right? E is h bar square k square by 2m. So each energy you can convert to a k. So this energy scale you can convert to a k scale also. But density of states is typically represented versus states versus energy. Okay?
Yes, sir. Thank
Sure. Are there any questions? All right. So with this, I'm going to move forward. I'm going to skip the density of states in 3D. We will take the same kind of steps. Instead of a circle, we take a sphere. We take one single step outside the sphere. Now you have a region. How do you find the area of or volume of the extra shell that we will have, which is 4 pi k square into dk divided by the volume of individual smallest k space that you can have. You will get the density of states, right? So now that we have density of states, we talk about a nearly free electron. So till now we saw completely free electron, right? We spoke only about plane waves. Now we take a plane wave and we say that the electrons are not totally free, but they are in a periodic potential. So they are in a weak periodic potential. Such a treatment is called as a nearly free electron. So electrons can be treated like waves with properties defined by a wave function, and they are in a potential which is periodic. So if we take plane wave solutions to this Schrodinger equation, which is e power I k dot r, the energy of them is h bar square k square by 2m. So obviously the energy versus k is parabolic, as we saw in the previous case. Now, what is the mass? How do you define the mass of this crystal? Electrons in a crystal do feel a small potential. That potential will change the electron energies as given below. But we will still approximate the electron energies to be parabolic in k. What we are saying is an electron which is free, which has a plane wave solution, has a parabolic dispersion. If the electron is taken to be in a periodic potential, it will change the way the parabola will look. But here we assume that it is still going to be a parabola. It is going to change how the parabola will be, right? So it is going to be either flatter or taller, depending upon the periodic potential and the strength of the potential. But we are still going to assume that it is going to have the parabola. And what changes the parabola is this effective mass. So we take the plane wave and we try to fit it to a parabolic solution by changing the exact electron mass, which was m naught, which is the free electron mass, by another parameter called m star. And this m star is called as an effective mass, which is defined as m star is h bar square into 1 by d square by dk, d square ek by dk square. This is easy to derive. You take this and differentiate E by twice differentiate E by Ek. So you first time you differentiate this, you get h bar square k by m. The second time you differentiate, you get h bar square by m. So this m goes here, so you get h bar square into 1 by d square ek by dk square. So this is what you will get if you differentiate this equation twice. So the effective mass is just an approximation of an electron in a periodic potential through a free electron potential. So we are still going to assume that the electrons are going to face, or electrons are going to have a parabolic dispersion. And if it's have a parabolic dispersion, the mass can be defined as such. This is an important aspect, but I will not go into this right now because we don't have the time for it. There is an important aspect of indistinguishability. So what it means is, if we have two electrons which are indistinguishable, we can only tell that the psi square is the same. Psi square is the wave function, and psi square is the only observable that you can have in quantum mechanics. If psi square is the same, this can be achieved in two different ways. Psi of R1 comma R2 is same as psi of R2 comma R1, which means I have two places R1 and R2, and I switch the blue in R1 and yellow in R2, or yellow in R1 and blue in R2. If the wave functions are exactly the same, irrespective of what I switch, then the psi will remain the same. Such particles are called as bosons. If the wave function are exactly opposite, if psi R1 comma R2 is negative of psi R1 comma R2, like this, then these particles are called as fermions. Why there are only these two cases? Because for two particles to be indistinguishable, these are the only two ways in which it is possible, right? That's why there are only two categories of particles. You have either bosons or you have either fermions. It depends upon what happens if you switch particles between two places. If the wave function is just exactly opposite when you switch, that way also there can be indistinguishable, or the wave function does not change at all even which you switch, right? So the normalize the wave function for the wave function. I mean, how do you now write this function? A psi which is a function of both R2 and R1, how would you write it? One way of writing it is like this, which will ensure that this equation is true. You can replace one by the other and then see that this is a way in which this equation can be satisfied. That's why a fermion wave function is written in this fashion. If there are two particles, if there are multiple particles, a way to write this is called as later determinants, but we will not go there now. Okay. All right. So we spoke about the density of states. Once the density of states, how do you populate these states? Can all the electrons be in the lowest lying state? or all the electrons can be in the highest lying state? How do you distribute themselves? The distribution is given by what is called as the fermion statistics. It's called as the Fermi-Dirac statistics. I spoke about the two kinds of particles, which is bosons and fermions, because each one of them follow one particular statistic. Particles in which the switching does not change the wave function are called as bosons. They follow what is called as the Bose-Einstein statistics. Particles which, when the particles positions are switched, when the wave functions are reversed, they are called as fermions, and they follow what is called the Fermi-Dirac statistics. And it is given by this, which is a function of energy, the chemical potential mu, and the temperature, which is given by 1 plus e power e minus mu by kBt. If you plot this function, the function will look somewhat like this. At 0 Kelvin, you have a flat function. As the temperature rises, it smoothens out. The electron statistics can be calculated if you multiply or do a product of the density of states into the occupational probability. The Fermi statistics tell you whether that particular energy level can be occupied or not. If f of e is 1, that means that the state is definitely occupied. If f of e is 0, that means the state is not occupied. And if f of e is anywhere in between, it tells you that it has an occupancy. It can be occupied or not depending upon the time. So if it is 0.5, it means half the time the state is occupied. Or if you have multiple number of states, you can say that half of these states are occupied in that particular energy level. So the density of states d of e tells you at e how many states that you have. If f of e is half, it tells you half the states are occupied, right? So it can, yeah, there are two ways to see this. So till now we saw that you have uh, uh, you have a crystallinity, you have periodicity, and you have some density of states which depends upon the dimension, whether you have 1 dimension, 2 dimensions, or 3 dimensions. The parabola is a solution. Each of these parabola are a band, okay, and these parabola are nearly free electron solutions. And if they have, let us say, on each of these, let me write. Now, let us take two Brillouin points, two reciprocal lattice points. Okay, these are separated by reciprocal lattice G. At each of these points, you have a parabola, right? These are nearly free electron solutions. At this point, you have another solution. Why do you have two? Because we saw from Born-Warman boundary condition that any change from the one reciprocal lattice should be the same when you take let's say one reciprocal lattice jump, right? From this point, you look at one point here. At this point, you take a G jump, the function should remain the same. So if you have a parabola at 0, you should have another parabola at G as well. This is what your symmetry or translational symmetry or crystallinity of the reciprocal space tells you. So I have a parabola at this point. I have another parabola at the first reciprocal lattice point. You can see that at some point here, which is G by 2, I will have wave functions which closely match with each other, right? At this junction, which is at the boundary of the Brillouin zone, or the boundary or half the reciprocal lattice vector, I have electrons from the first reciprocal lattice or first unit cell and the electron from the second unit cell having very similar k values. Under these k values, these electrons will interact perturbatively. This will lead to opening up of the gaps. You can look at this in two ways. One is this reciprocal lattice space way, or you can look in the real space. Take two atoms, different or separated by a reciprocal space R. Sorry, real space R. Okay, and you have several electrons, electron energy levels, right? And these electron wave functions, these are bound electron wave functions, right? So the electron wave functions look in this fashion, psi1 and psi2. When you bring these two electrons together, now you see that these two wave functions will meet, and Pauli's exclusion principle tells you that no two electrons can have all the quantum numbers the same, correct? As they come very close, now the Pauli's principle kicks in. These two electrons tend to see each other, and there are two states that they split up to. One is called as the bonding state, another one is called as anti-bonding state. So if the energy levels are like this, equal when they were far apart, as you come close by, the energy levels split, one in the lower state and one in the upper state. And each one of these states can take two electrons, remember, up and down, right? And this is what finally gives you an opening of the bands. So if we are talking about, let us say, the electron energy level in 1s, I suppose you all know about the hydrogen atom energy levels, right? 1s, 2s, 2p, 3s, and so on and so forth. If you take these 1s energy levels, as they come close, each one of these 1s energy levels will now split. And this is what you see here. So this is the interatomic distance. I have S, P, and so on. Right now I'm talking about 1s. As the interatomic distance reduces, the 1s energy levels now split. The same thing will happen to the 2s energy levels, right? So the 2s energy levels go like this. The 1s energy levels go like this. Oops, sorry. The 2s energy levels go like this. The 1s energy levels go like this. So at some distance A, there will be a gap in the states in which there are no states which are available. And away from this, there are a lot of energy states. And this gap which arises in an atomic separation A is the origin of a gap in a semiconductor. So you have a conduction band, you have a valence band. This is the definition of a conduction band, and this is the definition of the valence band. And the energy gap which separates them is called as a band gap, right? So you can look at the band gap origin in two different ways. In the real space, you can look at it because you have two electrons which are coming together. The Pauli's exclusion principle ensures that the electrons which are similar in energy starts interacting. Their energy levels will start to split up. Or you can look at in the reciprocal space, where electrons with similar k values from two different branches will interact. These similar k values will lead to waves which are called as standing waves. So till here they are called as plane waves. Very close to half the Brillouin zone, the plane wave which is traveling from left to right and the plane wave which is traveling from right to left will interfere, and k values which are very close will interfere more strongly, giving you what is called as a standing wave. So in the band gap, you have standing wave solutions because you have interference from k values which move from left to right and one which moves from right to left, right? So we saw the origin of bands from two different views. One is the real space view and another one from the reciprocal space view. If the bands are overlapping such that, so here you can have a material whose interatomic spacing is here, right? So if it is here, then you can see that the bands overlap. You have a metal. If it is here, then the bands do not overlap. There is a small gap, which is of the order of the thermal energy. You call it a semiconductor. And if the interatomic space is here, such that the gap is really large, in which the thermal energy cannot excite an electron from the low-lying band to higher-lying band, you call them an insulator. Right? You have different uh, kind of materials having different arguments. Once we have a band gap, we have a gap in the density of states, right? So we have a valence band which ends here, the conduction band which starts here. The density of states goes to zero. So you have to see this in a different way. The y-axis, the density of states is in the x-axis, right? You have a larger density of states just below the band, and the density of states drop to 0 at the edge of the band. The conduction band is 0 and this band gap, and starts to raise as the energy levels go higher.
Tab clean. Tab clean. Tab clean. Tab both.
Right? So you have the density of states and you have the Fermi level. You have the Fermi, you can draw the Fermi-Dirac statistics around the Fermi level. Why is this important? Because if you see the Fermi-Dirac statistics, you have the change in the Fermi-Dirac statistics only surrounding the Fermi level, right? So we have the density of states here. We have the Fermi-Dirac statistics changing around the Fermi level. The product of the two will tell you how many electrons and holes you have in which band, right? So the product of the Fermi-Dirac statistics multiplied by the density of states gives you electron here. If this will happen, this will have a small value if the Fermi level is at the gap. If the Fermi level is close to the conduction band, you have a larger electronic concentration. If the Fermi level is closer to the valence band, you have a larger hole concentration, which is given by N of E into 1 minus F of E. 1 minus F of E. F of E is the probability of occupancy of a particular state. 1 minus F of E is the probability of the state to be vacant. N of E into 1 minus F of E gives you the number of states which are vacant, which is the concentration of holes in a band, right? So while there is really a lot of material which is left to be covered, but I will stop here for the interest of time and ask if there are any questions. Are there any questions?
Sir, how effective mass is being calculated practically? I mean, you get values of effective mass of, let's say, silicon or gallium arsenide at 300 Kelvin directly in the book, and they are telling that it's being found practically. So, what is the practical experiment to find out that effective mass?
Good question. Really good question. I must really appreciate it. Let me answer that question for you. Okay. So do you agree that if I know E versus K, so this is E versus K, okay, energy versus K. Once I know E versus K, the slope of this curve is giving me the mass. Agreed?
Yes.
So all you have to do is to now find E versus K. And how will you find E versus K in an experiment? You do what is called as energy resolved spectroscopy, X-ray photoelectron spectroscopy, angle resolved X-ray photoelectron spectroscopy, ARPES. Okay, so what they do, they take a material and then they shoot X-rays. Electrons will be pumped out of this X-ray. Now you take this electron and then measure its energy and K, momentum. Once these two are independently measured, you plot E versus K for this material. In different case, see, it's very easy to draw this diagram in 2 dimensions here. If you draw the true band structure, you have to draw it along different directions. So typically people draw band structure along high symmetry directions, right? So you draw the band structure and along different directions, and then you take the slope of this band structure, you get the effective mass. And the effective mass is not a single parameter. It is typically defined in different valleys, different directions.
Okay, sir. Thank you. Next question is, in case of silicon, effective mass of electron is more than hole. Whereas in case of germanium or gallium arsenide, effective mass of electron is less than effective mass of hole. So how that comes? I mean,
it comes about because of the slope in the band. Okay.
Okay.
Now,
Okay.
so if the slope is large, then the effective mass is low.
Sir, will be less because it is
Will be
inversely
less.
proportional.
Exactly.
No,
So
sir. I am asking whether it's a rule kind of thing. I mean, electron effective mass will be more than hole effective mass, or that depends on the slope only, or experimental value only. Yes, yes.
So it is also a very good question. Let me answer that in this fashion. Okay. So here, do you see something here? So this is one situation where you have the valence band here and the conduction band here. Okay. Now, most of the time, it so happens that this region is flatter than this region.
Sir, you have not shared your screen. I
I'm
think
not
so. I cannot see.
Oh, okay. Sorry.
Now it's visible, sir.
Yeah. So look at here. You get a band gap here. You have the valence band here. You have the conduction band here. Correct? Now, depending upon the slope of this function here, you will get the effective mass. It typically so happens that the slope in the valence band or in these regions is smaller than the slope here. So you typically tend to have
Effective mass of hole.
lighter electrons and heavier
Yes,
holes.
yes, yes, yes.
It also has to do with the contributions. So if you actually calculate the band structure from tight binding, you can see that most of the time the valence bands are formed by p orbitals, and the conduction bands are formed by s orbitals. It so happens. It doesn't necessarily have to be so, but when you draw the tight binding model, each of these bands are formed by combination of atomic orbitals, and you will see that the valence bands are most predominantly formed by p orbitals. Hello. Yeah. Sorry, did I answer your question?
Yes, yes, sir. Yes, sir. I got it. Thank you.